What if we want a model that not only groups data or makes predictions based on basic patterns, but can actually learn complex relationships all by its own, like recognizing faces in photographs or understanding speech? This is where deep learning comes in. Unlike traditional models that rely on simpler patterns, deep learning models can actually handle massive amounts of data and learn deeper, more complex features all by themselves. Think of it as a model that doesn't just group apples and bananas, but can also tell you if it's a red apple or a green apple. Deep learning uses a type of a model called neural networks, which are inspired by how our brains work. These models can learn from raw data, figure out complex features, and make predictions that are far more sophisticated than traditional models. Ready to see how these deep learning models work? Let's dive in. Imagine a model that has never seen a panda before, but can learn what one looks like piece by piece, layer by layer. Deep learning is like teaching a toddler what a panda looks like. You start by showing some basic pictures. Look, here's a panda. The toddler might not understand it at first, but as you show more and more examples, they start recognizing the round ears, fluffy fur, and the black and white patterns. Similarly, deep learning models are like layers of learning, where each layer builds on the information learned by the previous one, in a step by step process that gradually helps the model understand more and more complex features in the data, whether it's images, text, or sound. Let's take our panda example and see how this works. Layer 1, basic shape detection. The first layer is super simple. It detects the most basic features like the lines on the panda, the edges on the panda, or the color patches, in this case, black and white. It doesn't know what it's looking at, it's just analyzing the building blocks of the image. Layer 2, patterns and texture detection. Now things get more interesting. This layer takes the simple shapes from layer 1 and starts identifying patterns and textures, like the fluffy fur or smooth areas of the panda. It passes this richer information to the next layer, body parts detection. By now, the model is starting to recognize more defined features like ears, eyes, or the overall round shape of the face. The pieces are coming together, but the model isn't ready to make a final call yet. It passes this understanding to the next layer, larger parts detection. This is the final stage where the model begins to see the bigger picture. Literally, it starts recognizing larger parts like head or arms and begins piecing them together. It's now ready to ask the big question: is this a panda? Here's the really cool part. Each layer passes its findings to the next layer, making the model understanding deeper with each step. But it doesn't end there. Once the model makes a prediction, like this is a panda, and again, remember, it's a supervised training where there is a labeled information. When it asks if it's a panda, it's checking against the label which is predefined. It checks if the prediction is right or wrong. If it is wrong, the feedback is sent back to the earlier layers, telling them to adjust their understanding. So every time a model makes a prediction, it learns from its mistake. This feedback loop is what helps deep learning models become more accurate over time, layer by layer. It keeps learning and refining its knowledge until it can confidently say, yep, that's definitely a panda. Deep learning layered approach is what allows these models to take on complex tasks like recognizing faces, detecting objects, or even driving cars. In conclusion, while deep learning models have the incredible ability to process large amounts of data and pick up on intricate patterns, they still have a way to go before they match the quick learning capabilities of a toddler. A child can learn from just a few examples and generalize across different contexts, whereas deep learning models often need like thousands of images to reach a similar level of understanding. However, where deep learning shines is in its capability to handle vast data sets and continuously refine its understanding over time. As technology advances, the gap between human and machine learning is narrowing. But for now, there is still something special about how effortlessly toddlers can learn. So while deep learning methods or models may be powerful, they're still learning from us in more ways than one. Now let's dive into what happens inside a layer of a deep learning model. And we will start with the idea of neurons. Imagine neurons in a deep learning model as a tiny decision maker or worker in an assembly line. Each worker, neuron, has a specific job. Some might be looking for certain patterns like lines or colors, while others might be on the lookout for more complex features like shapes or textures. But here's the twist: every worker's decision isn't equally important. How strongly a worker's opinion or a signal matters is determined by something called weights. So, how do neurons work? Picture neurons like light switches, but not just like those on off switches. They are more like dimmers that can adjust on how much light or signal they can send. Every neuron fires, but how bright it shines or how strongly it signals depends on its weight. Here's a simplified analogy. Strong signals, like a bright light, comes from neurons detecting something very important, like black fur on a panda. Weak signals, like a dim light, comes from neurons picking up less important details, like a tree in the background. Now, the interesting part, the weights. Think of these as dials that adjust how each neuron's opinion counts. If a neuron detects something critical, like panda's distinct round ears, the weight dials up, making its signal louder. But if it picks up on something less relevant, like a random shadow, the weight might dial down, so its signal is softer. The coolest part? Neurons learn over time. When the model makes a mistake, let's say it misidentifies a raccoon as a panda, the model gets feedback and goes back to adjust the weights. It's like telling a worker in the assembly line, hey, you put on too much importance on this detail. Next time, dial it down. Over the time, the neuron gets better at their jobs. Start making more smarter decisions. Imagine you're showing a model different pictures of pandas. Neuron A is looking for black fur and notices a lot of it, so it fires strongly. Neuron B is looking for round shapes, maybe the ears, and fires, but not as strongly because it only sees a few curves. Neuron C is watching the background, say some trees, and it fires weakly because it knows the trees aren't as important in identifying the panda. Once these neurons combine their signals, the model decides, yes, this is a panda. But if it was strong, the model adjusts, telling the neurons to dial up or dial down their signals next time. Neurons fire based on what they detect, but how much they contribute depends on their weights, which are fine tuned through feedback in the process of supervised learning. By learning from labeled examples, the model improves over time, adjusting its neurons and getting better at making accurate predictions. Is like having a team of workers getting smarter with every task they complete.